Hello, hello. Hmm. Hello guys, we will be discussing. Wait a second. Hey guys, we will be discussing in this video, in this stream, the educational code forces round 186, which was held today. So, let's start with the problem. We will be discussing from 8 problems A to E. This is the first problem I would be discussing New Year string. Hmm. So let's read the problem statement first. We will call a string consisting of character 0 to 56 a New Year string if at least one of the two condition is met. So a string is called a New Year string if at least one of the two conditions is met, and those two conditions are, first of all, we need to see that the string contains only character 0, 2, 5 and 6. So it is called a New Year string if only two conditions are met, and these two conditions are, it should contain 2026 as a continuous substring, which means like the string should be like something like this, 2026, and here it could be anything, here it could be anything, or it does not contain 2025 as a continuous substring, which means so the first condition says the string should be something like this. Here it could be anything, it could be anything, just 2026 should be a continuous substring. Or another thing, it should happen, or one thing that does not, this should not happen, like 2025 and this. So this should not happen, or this should happen. Both of one of them should hold true. So we need to convert a given string. We are given a string S, and now we need to make it to a good string. And good string is held by these two conditions, which I have marked above. So we can choose so how do we change a string? We choose a character, any character S, and replace it with any other character 0 to 5, 6. Only these four characters. So we need to get the minimum number of operation. We need to make the string good. So first of all, I can surely say that I can make a string good in at least four of the operation, right? Like if the string contains if the string contains any character, like these are the characters in the string. Now I can just convert this character to 2, this character to 0, this character to 2, this character to 6. In worst case, it would be four operation, not more than four operations, right? So if we do like this, the first condition would be held true. Or how can I make it good? So let's say if the string was like 2, 2 2 2 2 2 2 like this. So in this, how many operations do I require? I require only two operations, not four, because I can change this to 0, I can change this to 6. So now I get a string like 202622. Now I get a substring 2026. So we can brute force on this. The string is very small, or even if it was not small, I can just brute force on. We are only concerned with the four characters, four consecutive characters. So if the four consecutive characters, I can try to make it 2026. What I mean by this is x x x x x x. This is the string. So what I can do, I can try to make this 2026. If this or after that, I can try to make this four character 2026, or after that I can try to make these four character 2026 2026. So whichever holds the least number of operation, that is good for me. So for example, let's take a string like this. Let's take this as the string. So if I take this as the string, mm, so in this I can try to make this as 2026 2026. So how many operation do I require? Only one operation, because this is equal to this is same, this is same, this is same. Only this needs to be changed. So one operation. Or or I have to remove 20, or I have to remove 2025 as a consecutive substring. So this contains 2025. So if I change it to anything else, like if I change it to anything like 2022, still this would be a good string because it doesn't contain 2025 as a consecutive substring. So this is a good substring. So just we need to brute force on the four characters. Either we make it to 2026 or we do not make, or we, if it is 2025, we make it bad. So we change any of the character 2025 to 2022, 2026, anything would work. So another thing we can probably notice is like if the string already contain 2026, it is already good. But if the string contain 2025, so if it contains 2025, we just need to change we just require one operation. That one operation is changing 5 to 6. So this would become 2026. So inverse, or if it doesn't contain let's say it doesn't contain 2026, it doesn't contain 2025, then string is already good, because if it doesn't contain 2025, the string is already good because of the second condition. So I can say that inverse only at max one operation would be required. When will I require one operation? When it contains 2025. And when will I require zero operation? When it already contains 2026. So these are the two conditions which we need to check in, which we need to check. So we can just iterate on the four characters. So I have done in bit different fashion, but we can just simply check that if the string contains 2025 or 2026. If it contains 2026, then answer is 0. If it contains 2025, then answer is 1. So you can check also my code in this. What I have done is, if I am checking the four consecutive characters, si plus 1, si plus 2, si plus 3. So what I am checking is, I am checking if si like if it contains 2025, then we need to change this. And so I am maintaining a count variable, like how many 2025 are there, now we need to change them. Or if it already if it doesn't contain 2025, now I am trying to make it to 2026. So if it is not 2, I need to change. If it's not 0, I need to change, not 2, change like 2026. So if they are not matching, I need to change, and there would be a one operation increase. So these are count 1 and count 2, and minimum of those I can return. So this is a bit complicated code. The approach I told you earlier was much simpler, like answer would be 1 or 0 only. Okay, so like this was a fairly simple question. Let's move on to the second question then. So second question is New Year cake. So in this question, this is also a nice question. The cake contains monocarp is going to bake a New Year cake. So cake must contain at least one layer. It may contain at least one layer. The size of top layer will be one. So cake is something like this. Like we have a multi-level cake. So cake is something like this is first level, this is second level, this is third level, and this is fourth level, and so on. First level, second level, third level, fourth level. This is our cake. So first level has it is given that first level has width. The area of the first level is 1, then area of second level is 2, area of third level is 4, area of fifth level is fourth level is 8, area of fifth level is 16, and so on. So what do we need to do? We have a total e to k. So it is given that if the layer, let's say the layer has size k, so monocarp would require k kilograms of the chocolate. So if it has size 2, we need 2 kgs of chocolate, we need 4 kgs of chocolate, we need 8 kgs of chocolate, and so on. So uh, exactly one chocolate. So if we are going to be covered in one chocolate. So we have two types of chocolate, black chocolate and white chocolate. So second layer should have exactly one layer, one chocolate, either black or white. So which means if I am going to cover second layer, which means I would be require either 2 kg of black chocolate or 2 kg of white chocolate. Anything of those. Okay. So this is one rule. Rule number 1 is the layers are in increasing powers of 2, 1, 2, 4, 8, 16, and so on. Second rule is that we need exactly same kgs of chocolate as in the layer, as the layer is having the weight also. And the third rule which is given below is that both the layer directly below it and directly above it must been covered with white chocolate or vice versa, which means the layers must be alternative. So which means that if this is a black layer, then this should be a white layer, and if this is a white layer, this should be black, then white. So layers should be either black, white, or white, black. So these are only two possibilities. So what do we need to output? What is the output of the what is the answer for this? So answer is how many layers can I at max make. So what is the limitation? Limitation is we are having at exactly a kg of white chocolate. Let me see, white or black. A kgs of white chocolate and b kgs of black chocolate. So these are our limitations. Like we are fixed number of white chocolate and fixed number of black chocolate, and we need to make a cake such that it is black, white, and it should be in increasing powers of 2. Okay. So, like there are not many choices we have. We can either make the cake in this type, or we can make in the cake a cake in this type. So if these are only two choices, so we can try to make cake by this fashion or by this fashion and see what layers are we having. Let's say I am having L1 layers here, and I can have L2 layers in this type. So whatever the maximum of those, I can try to make, I will make cake in that fashion. Okay. So what do we need to do? So first of all, I mark the layers like this: 1, 2, 4, 8, 16, 32, 64, and so on. And now I first try to type 1. What is type 1? Type 1 is black, white. So what so which means like b minus 1, then here it would happen a minus 2, then here it would happen b minus 4, then here it would happen a minus 8, like so on. We are making cake in this style. Or like we can try to make type 2. What is type 2? White, black. So if this is type 2, we can try to make cake like this. So this is a white layer, so white should be painted with a chocolate, so a minus 1. This is a black layer, so it should be painted in the black chocolate, which is b minus 2. It requires 2 kgs of chocolate. Now a minus 4, b minus 8, and so on. So we would stop at a point where we don't have sufficient chocolate. Like here it requires 8 kgs of chocolate and we have only 7, so we need to stop here. We can't make this layer, so answer would be 3 in this case. So we simulate this and check whichever way we are getting more number of layers, we make the cake that way. So that is exactly what I have done in my code. So code is bit long, but it is mostly repetitive part, so I can explain you from one by one. So this is A and B. So this is A kgs of chocolate and B kgs of chocolate. A kgs of white chocolate and B kgs of black chocolate. So this is count 1, count 2. This is layer 1. Count 1 denotes number of layers we can make by first type of cake, and number of layers we can make from second type of cake. So layer 1 or layer 2, which I marked earlier. And done A, done B denotes number of kgs of chocolates we have used. So done A means a number of kgs of white chocolate used. Done B denotes number of kgs of black chocolates used. And turn denotes which layer is this. Is it a black layer or is it a white layer? And level denotes which level are we on. So level, which means that how many kgs of chocolate would be required on this level. So level would be multiplied by 2 at each level. Okay. So if turn is 0, so I have denoted if turn is 0, which means this is the white layer. So this means here I can mark it, this is a white layer. If this is a white layer, so I would be requiring level amount of chocolate, and done is the chocolate I have already used. So if done A plus level, so if I have already used 5 kgs of chocolate, and I here require 4 kgs of chocolate, so which means total it would be 9 kgs of chocolate. So this total should be less than equals to A, so that I can use this. So this is what I have done. If done A plus level, so this is a chocolate already used, this is chocolate we need to use. So this should be less than total. So already plus current should be less than total. So in that case, we can paint this layer by white chocolate and we move further. So how do we move further? First of all, count 1 increases by 1 because we increased one layer by type 1 of cake, and turn changes to white to black. So turn XOR 1 means if it was 0 it becomes 1, if it was 1 it becomes 0. So turn, I have XORing turn by 1, which means switching black white white black. And level increases by 2. So if this level has 2 kgs of cake, 2 kgs of chocolate required, now next level would have 4 kgs, and if after that 8 kgs, 16 kgs, and so on. And done a plus equals to level, which means total now increases by current what we need currently. So this is for the white part. And if we can't do this, if it is greater than, like we don't have enough chocolate, we break from here, like we can't make more cake, more levels of cake from this type. Now we do similar thing for the black part. So if turn was of 0, here it would be means if turn is of 1. So if turn is 1, which means this is the black layer, and we are doing similar things for black, which means uh, turn B was total chocolate used for black, and level is the current amount of chocolate we are needing. So this should be less than total chocolate of black which we are having. And we increase the done b by level increases by 2, we take the XOR and we increase the count, and so on. So same thing we have to do, like this whole part we have to do again for now, but starting by level equals to 0. Here we are starting with turn is equals to 0, which means that this first part is of white. Now if I start with turn is equals to 1, which means the first layer is now of black. Here the first layer should be of black, and here should the first layer should be of white. So white black, and here is black black white. So this is only difference, and difference here is now all the things above are same. Now just I increase the count 2 because this is cake of type 2. So I increase the count 2 by 1, and I keep doing this. I keep simulating. I try to add white chocolate, I try to add black chocolate, white chocolate, black chocolate, and if it is not possible I break from there, and at last I output max of count 1 and count 2, which is maximum chocolates, maximum layers we can make from either type 1 of cake or type 2 of cake. So that's it. I hope this the explanation was clear. Now we can move to the third problem, I guess. So third problem is production of snowmen. The problem statement is a bit complicated or maybe a bit on larger side, but the problem is fairly interesting, I would say. So the problem is start with there is a snowman and it consists of three snowball, head, torso, and leg. So which means the snowman has head, has torso, and has leg. So what are the rules? The rules should be the ball forming the leg must be strictly larger than ball forming the torso. So which means the snowball weight of snowball of leg should be greater than weight of snowball of torso, and weight of snowball of torso should be greater than weight of snowball of head. So L should be leg should be greater than torso should be greater than head, which means like if I am using one amount of snowball here, so I need to use 2, 3, 4 or anything greater, and if there is I am using 2, I need to use something larger, 2, 3, 3, 4, 5, 6, anything larger. So let's say 5. So this is a valid snowball. Okay. So we are given three conveyor belts. So conveyor belts, which means A, B, and C. The rule is A should be A greater than B greater than C. We need to remember this. This is head, this is torso, this is leg. So A should be greater than B should be greater than A, and C should be greater than B. Okay. So what it says that there are three conveyor belts. So the conveyor belts are like this. This is conveyor belt A, this is conveyor belt B, this is conveyor belt. Let's not make here. Let's make here only. So this is conveyor belt A, which means this is the conveyor belt of head. This is conveyor belt B. This is conveyor belt of torso, and this is conveyor belt of C, which means this is leg. So the rule was A greater than B greater than C. Hmm. Now the conveyor belts are this, and they are cyclic, which means like this. Let's say there were let's make it with white. So these were the snowball. One, two, three, four. Okay, so which means that after four, one comes again. So like the snowball one comes, then two comes, then three comes, then four comes. Or if we start with the snowball two, so let's say we start with snowball two, then two comes, three comes, four comes, then again we go in a circular fashion and one comes. Okay, so let's mark one, two, three, four here also, and one, two, three, four here also. We need to pay attention that all these have n snowballs, same number of snowballs. Hmm. And this part explains that how it is circular. Like after n, there comes one again, then two, three, four, then n, then one again. So to produce snowman, it is necessary to specify three parameters I, j, k. So what does I, j, k denotes? Let's say I say I is one. Let's mark it with pink color maybe. I is one, j is two, and k is four. Let's say I have marked I is equals to one, j j is equals to 2, k is equals to 4. What does it mean? So this means I, j, k, which means that this is the first snowball. 1 2 4 is the first snowball. 1 2 4 is the first snowball. Then what is the second snowball? Second snowball is next of this. 2 3 and in circular manner 1. 2 3 1. 2 3 1. What is the third snowball? Third snowball is 3 4 and 2. 3 4 2. And what is the fourth snowball? Fourth snowball is 4. Now next of this is 1 and next of this is 3. So what was it? 4 1 3. So these are the four snowball made. So if I say ijk is this, so these are the four snowballs made. And how many of them are valid snowball? What was a valid snowball? Where a head was a c should be greater than b and b should be greater than a. I can write it here again. A greater than b greater than c. So which of these is valid snowball? Is this a valid snowball? Yes. 1 greater than 4 greater than 2, 2 greater than 1. Yes, this is the valid snowball. Is this a valid snowball? No, because one is not greater than 3. Not valid. Is this a valid snowball? No. Is this a valid snowball? No, because this is wrong. So we get a once valid snowball. So in this, when I choose I, J, K in 1 to 4, we only get one valid snowball. But the question requires that we have to choose I, J, K such that all four snowballs are valid. What does it mean? Like all four of these snowballs which I have made should be valid, should be marked tick, because for all this should satisfy A, C greater than B, B greater than A. Okay. So this was not a valid choice of IJK because only one of them was correct. We need all the four, all n choices to be correct. So we need to output the number of possible choices of IJK which can make all the snowball choices correct. Correct means C greater than B, B greater than A. Okay. So let's see by an example. First of all, we need to pay attention that n is 5000. So if n is 5000 and we need to output three parameters I, j, k. So what can I say? What can I say from looking at the constraint? That it would be something of n square type, because 5000 usually allows us to go n square or n log n square, which means there would be some sort of two loops which would be iterating on and comparing the values of. So this is just some hint. Let's try simulating or dry running one of the cases and we would get better idea of how it's working. Hmm. So let's say these are the snowballs and let's mark them by A. This is A, this is B, this is C. So first of all, I want to say that I can treat them separately. Like the condition was A greater than B, B greater than C. So can I make the condition in two parts? This is first condition and this is another second condition. So I would be treating both the conditions separately. So I would be first checking how many pair set of I comma j satisfy such that A is greater than B for all of those. So first of all, I would be picking the valid choices for I and J only. Then I would be picking valid choices for J and K only. Now I can multiply those. So let's say possible choices for I and j was three number of possible choices here are holding, and there are two number of possible choices holding. So can I say I can have total six number of possible choices, because three pairs from here and two pairs from here. From P and C I can say that we in total I can have six possible choices of A, B, C. Okay, we would get a better idea from the example, or if we try run uh, this only, let's try than this only. So first of all, I am concerned only with these two layers, A and B. So can I say this and this is a good choice? No, because if I do this 4 and 4 is not greater than 4. There is strict inequality. So this is not a valid choice. So this is not a valid choice. Now let's try this choice. 1 and 4. Is this a valid choice? 1 and 4, yes, this is good. 4 and 5, yes, this is good. 2 and 7, yes, this is good. 3 6, yes. 5 6, yes. So all of B is greater than A in all these pairing. So I can say yes, this is a valid choice. So one valid choice is I is equals to 1 and J is equals to 2. Okay, let's try to figure out another possible choices. So this, oh, so let's mark it now pink by pink. So is this a valid choice? 1 5, yes. 4 7, yes. 2 6, yes. 3 greater than 6 greater than 3, yes. 5 greater than 4, no. This is not a valid choice, because all of them were holding, but this thing 5 greater than 4, this was not holding, so this is was wrong. So let's now try this. I is equals to 1, j is equals to 4. Is this a valid choice? Yes. How? Not yes. Let's try to figure out. Is 7 greater than 1? Yes. 6 greater than 4? Yes. 6 greater than 2? Yes. 4 greater than 3? Yes. 5 greater than 5? No. This is not a valid choice, because this is not holding true. Okay, now let's try for I is equals to 1, j is equals to 5. Yes, this is good. 4 greater than 6, 6 greater than 4, yes. 2 greater than 4, yes. 3 greater than 5, yes. 5 greater than 7, yes. Like this I said in reverse order, but yes, 7 greater than 5, 5 greater than 3, 4 greater than 2, 6 greater than 4, and 6 greater than 1. Yes, these are valid choices. So another valid choice is I is equals to 1 and j is equals to 5. So this is also a valid choice. So if I have got two valid choices, now can I say that this is not exactly one choice? These are five choices. How? Because if I can choose I is equals to 1, j is equals to 2. So can I also say I can choose I is equals to 2 and j is equals to 3, because they are same thing. We are only concerned with the gap. So the gap here is 1, the gap here is 4. So yeah, we are only concerned with gap. So I is equals to 1 and j is equals to 3 also has one gap, because if we are pairing with this, so we were already pairing with this. So if we start with this or we started with this, it doesn't matter, because we are ultimately getting the same pairing. So which means a pair, if I get a pair of ij, it is not a single pair, it is actually n pairs. So these are n pairs. How are they n pair? I can write like this: 1 2, 2 3, 3 4, 4 5, and 5 1. These are five pairs I can get. So these are not exactly one pairing, these are exactly five pairing. Like similarly for 1 5 I can write 1 5, 2 1, 3 2, 4 3, and 5 4. These are five pairings I can get. Hmm. Okay. So these were the five pairing if I can get. So what I can say is, if I can, so can I, first of all, my question is, can I get some these pairing like how I simulated I1J2 and I1J5? Can I simulate and get those counts? How many valid counts are we having? Yes, I can simply get, because we are allowed n square. So we are just, let's first of all remove this part. Okay, so we are just concerned with these two vectors. So what I can do is I can maintain one pointer at this start place, and now I can move another pointer from this location. So if these are two pointers, now I can compare respective values. 1644253756, like how I was comparing. So this is O of n for one comparison, and we are doing n comparison, so this is n square. So by n square, by n comparison, I can get how many counts of valid ij. So ij pairs, how many ij pairs are there. So similarly, can I get how many valid jk pairs are there? Yes, like what I was doing for a and b vector, I can do similar thing for j and k vector, and I can get the valid jk pairings. So ij pairings I can get jk pairing. So these are ij pairing, these are jk pairings. I can repeat again, how would I get those pairing? So I would maintain a pointer. First of all, outer loop would be iterating on this. So this is outer loop. The pink pointer, the pink mark is outer loop. So now once we get the two pointers, the first pointer is fixed at first position, and second pointer would be our outer pointer and moving from these to this. So this is first one pointer and this is one pointer. Now I would compare the respective values 1644253756. Like in this would be an inner loop comparison of n values 164427. If any of the pairing is bad, like this was a bad pairing, so I can reject this and won't increase my count. But let's say this was a, now from this the pointer would go on to this. Now what would the pairings be? 14452736 and 56. So this is a good pairing because no ij pointer was bad, so I can increase my count by 1, count plus plus. Now I would do similar things for these bj vectors and bc vectors and get my count. Okay, so if I have got my count 1, which is number of ij pairings, or let's say ab pairings, and count 2 as bc pairings, a pairing of B and C and A and B. So if I can surely say I have to multiply, but I also have to multiply n with them, because as I said earlier, like if I say I j is equal to 1 2, it is not exactly one pairing. These are total n pairings. Why? Because I marked them earlier. Because if we are doing this, if I can start with 1 2, I can very well start with 2 3, because the difference is same. Difference of, because if I was taking this was already being taken, so it doesn't matter, I can start with 1 4 or 4 5, it is the same thing. So there would be n more pairings like this. So n into count 1 into count 2 would be my final answer. So hope you have got this part, like how we are actually calculating count 1 and count 2, and how the formula of n into count 1 into count 2 is coming true. So here, like here the count 1 was, like in this question, this count 1 was would be 1, count 2 would no, we already got count 2. So this was count 2 would be 2, count 1 would be 1. So and total n was 5. So 5 into 2 into 1, which made it 10. So here, like in this part, so n is 3, count 1 is 3 because all pairings are good, and count 2 is 3 because all pairings are good. So 3 into 3 into 3, which makes it 27. So let's come to the code and try to see how we are actually doing it. So first of all, take three vectors input. This is count 1 and count 2. So this is outer loop. The outer loop is the starting position of b vector. Starting position of a vector is fixed. This is like this was a vector. This is, if this is a vector and if this is b vector. So starting position of a vector is fixed here, but starting position of b vector would be varying. First it would be this, now then it would be this, then it would be this, which means first pairing would be 1 1, then another pairing would be 1 2, then another pairing would be 1 3, then another pairing would be 1 4. So these are the pairings, and now I need to check if this pairing is good. How do I check? I iterate in the iterate I check for n elements. This is I am checking for n element, and n elements, the b vector should be increased by I. So like b vector should be, let's, if the I was 2, so b vector should be increased by 2, and I need to compare this and this and this and this and so on. So if at any point this the condition of a greater than b is false, this is a wrong condition. So we need to stop here, and the flag is false, which means this is a bad pairing. And if flag was true, Flag was initially marked true, and if flag hasn't been turned off at any point, so which means flag is true, and I need to increase my count and count 1 plus plus. Same thing I am doing, but for vector C and B, and if this is holding true, I increase my count to. And now at last, if the total answer would be n into count 1 into count 2, because count 1 into count 2 pairings were there, but actually there were n more n multiplied pairings, because 1 to because ij pairings can be multiplied by n times, because we the start point doesn't matter, because 1 2 is same as 2 3, 2 3 is same as 3 4. So if ij I can, if I say ij is 1 comma 2, then ij can very well be 2 comma 3, because we were not checking only, we had made a pointer fixed at 1, but a pointer could be at 2 as well, but we were not doing this because we were reducing. If we starting doing that, then it would become of n cube, which was not allowed. So this thing can be said like this can be n square, and then we can just multiply n and we can get our total count. Hmm. Okay, so now I hope the C problem is clear. Now we can move on to the fourth problem. Okay. So this was, I can say, also maybe a slightly interesting problem, or I struggled on this one. Uh, the constraints are a bit nice. I don't understand what makes these constraints different. Like it could be very well be n is equal n could be 1e5 as well. So what are we given here? So there are a group of n people decided to decorate a Christmas tree. So they are having n plus 1 boxes of decoration, number from 0 to n. So if we are saying n is equals to 4, which means we are having actually 5 boxes, 0 1 2 3 4. Okay. So person 1 P1 takes a decoration from it. So this is the tree, and we need to decorate it, and we need to add the decoration from these boxes. So person 1 has two choices. Either he can take decoration from here and add here, or which means take decoration from box 0 and add here, or another choice is take decoration from box 1 and add here. Okay. Hmm. So person 2 has also same choices. He can take decoration from box 0 or take decoration from box 1. So this is or condition, like he can do this or this. Similarly, this person 3 is also these choices, this and so on. So during this process, there should not be a condition situation where person needs to, like person I has two choices, either take from box I or take from box 0, and if both boxes are empty, so he can't decorate the tree, and those situations should be avoided, and permutation would not be fair. So person 1 takes from box P1, person 2 takes from box P2. So if I say that person P2, let's say second person is not able to take either from box P1, from box P2, or from box 0, which means box 0 is also empty and box 2 is also empty, which means that person 2 is sad, which means he can't decorate the tree, and this permutation is bad. The choice of permutation is bad and we should avoid it. So at last we need to calculate how many permutations are good. So first of all, we need to make some observation, or list some observation, like what would make a permutation good. So what would make a permutation good? This is our question. So first of all, can I say that uh, also I forgot to mention that this is going in a circular fashion, like 1 2 3 4, he decorates, 1 decorates, 2 decorates, 3 decorates, 4 decorate. Now again 1 has to decorate, 2 has to decorate, 3 has to decorate, and decorations should go on till all the decorations have been completed, which means there were total a0 plus a1 plus a2 decorations, and we need to plus a and decoration, we need to spend all of them. So it should not be case like A2 is not able to decorate because this his box is empty and zero box is empty, but there are some decoration left, like let's say AN has some decoration left, so this should not happen. Okay, so what observations can I make, like what can I say when the permutation would be good, it would look something like this. So what it would look like, first of all, can I say permutation would ever look like 1 4 3 like 1 4. So this was 0. Let's leave the 0 box for once. Let's assume there is no 0 box and these are 1 2 3 4. Can a permutation look like this? 4 5 3, let's say 4 5 3 3. No, I would say no, because let's make them smaller. It would be easier to understand. 2 3 2 2, like this. So I would say this is a bad permutation. Why? Because person one decorates, yes, okay. Now we have one decoration left. He decorates two decoration left. He decorates one decoration left, and he decorates one decoration, which means like he was having two decoration earlier. He decorates, and now he have one decoration left. From three, it got reduced to two. Two got reduced to one. One and two got reduced to one here also. Now we come here again. Now zero decoration left, one decoration left, zero decoration left, zero decoration left. Now comes again his choice. He can't decorate, but there is still some decoration left. So this is wrong. So I can say that like increasing thing. If there is any increase in the permutation, so that increase. So here now he would beg. So he would go to box zero, like I don't have my own decorations left, so can you borrow me some, because I need at least one decoration so that person 2 can decorate complete his decorations. Okay, so I would say that the game would be fair to go like, first of all, everyone decorates their own decoration. Then they ask for the zero box. So first of all, no zero box would be used. First of all, he would complete his he would exhaust his own decoration. Then he would exhaust his own decoration. Similarly this, because it doesn't make sense to borrow from someone when you have own money. You borrow from someone when when you don't have your own money. So similarly, like when you don't have your own decoration, then you go to borrow to zero. Okay, so first of all, this would be exhausted, and it would go like, it would exhaust like this. So what how can I change completely to this? So this would be max minus this. For example, the numbering was 1 4 1 3. So then it would become not max minus this, it would be minimum reduced to zero, which means like minimum here was zero, so at least minimum here was one, so one round can happen like 1 3 1 2, this would be 0 2 0 3 0 2. So because the minimum was 1, which means we are guaranteed that one round would happen, so one round would happen. This would reduce to 0, 1 reduce to 0, 4 reduce to 3, 1 reduce to 0, and 3 reduce to 2. Okay, so if I can, I say now comes the part of borrowing. So how many times he need to surely borrow? He need to surely borrow three times, because it has demand of three, so he need to borrow three times for sure. So plus three. So zero box should at least have three decorations. Okay. How many decoration does he need to borrow? He does for like he need to borrow three decoration. How many decoration does he need to borrow? He doesn't need to borrow anything, because he has the maximum number of decoration. Why would he borrow? So game would end at his part, like game would end at this part. So how many decoration does he need to borrow? He need to borrow two decorations, because the next person is two decorations. So game would something go like, let's say if he borrows two decoration and he borrows zero decoration, because he doesn't have to go more, and so it would go like 3 3 2 2. So if it has happens like 3 3 2 2, so what would happen, like he would decorate, then decorate. Now he would decorate, he can decorate. Now he doesn't need to decorate because the ahead there is no decoration, no one has a decoration left, so why does he need to decorate? Okay, so can I say finally the increased part, can I say finally the difference should be, difference of maximum and minimum should be at max 1? Why? So if I say that, say somewhere here in array is 5 and somewhere here in array is 3, so which means that there he need to decorate for two more rounds than them. Like if he can decorate for 3 rounds, he need to decorate for 5 rounds. But this can't happen because if he decorates, he can either decorate or non-decorate, but for at max one time. For example, if he decides to not decorate, so if he decides to not decorate, so he can't also decorate because the game ends there. If someone decides to not decorate, like I can mention here, I can list some observations here. First of all, observations. First observation is, uh, if someone decides to not